Hi, I'm going to talk about a machine learning predictive analytics demonstration where I'm going to try and predict the price of gasoline next week. My name is Martin Madsen. I have a PhD in experimental physics and 16 years experience working with sensors, data collection, data analysis, and all kinds of different predictive model building. The demonstration today is an example of using a variety of different inputs in order to predict a useful output. I'm going to look at input prices, imports and exports, in current inventory and production, and join all of those together in the oil industry in order to predict the price of the gas price at the pump, at least the average gas price across the United States for gasoline for the coming week. So given a set of situations, a set of circumstances, how are these going to impact what's going to happen in future time? The data are coming from the U.S. Energy Information Administration, which publish a variety of different statistics and data for the United States retail gasoline prices, the spot price oil for crude oil, the production of the crude oil in refineries, the imports and exports, current stocks and supplies on a weekly basis. So I take the current information from the prior week and I use it to predict the current week's average gasoline price in the United States. I've worked on productionalizing this solution so that I'm using the Azure Data Factory so that this is set up to be an automatic system where the Azure Data Factory will draw in data from web tables from the Energy Information Administration and send them to blob storage on Windows Azure. And I'm going to show the pipeline architecture as I'm going throughout the course of this demonstration. On this first piece is the part of the architecture, the part of the pipeline where I'm pulling in the data. There's about 8 or 9 different web tables that I'm skimming in order to pull this data together and send it to the Azure Blob. This is what the data table looks like after I've pulled the data off of the websites and put them into Azure Blob storage. And it's semi-structured data. I have information about the date and the location, the type of data that I've got, and the units on each of the different pieces of information. And I'm relying on the dates here to join the data together. So I'll look at each piece of data and join it by the first day of the week, and that allows me to connect all the different data sets together. From there, I have a pig script that's processed on an HD Insight cluster. The Data Factory spins up the cluster and then runs the script on the data, which allows me to clean, process, and join the data sets together so that I have them in the way in which I need them in order to do machine learning on them. That's an HD Insight cluster that spins up on demand each week when I run this process, which is set up to run automatically once a week. This is what that looks like. It pulls in the data from the different Azure blobs, and it actually outputs 2 different pieces of information. It will output historical features that I use for training the model, and then it'll also output a handful of recent features for testing the model. And I'm also outputting historical gas prices and recent prices, and what I've done is essentially split off the last few months of data. And so I'll create my model based on about 10 years worth of data and then use it to predict the gas price for the last month or so to see how well the model is performing. So I have historical features that then get joined together, and again it's semi-structured data, and I have a schema that keeps track of all the different columns and what they mean. Once I have that data, I then send it off to the Azure Machine Learning, the Azure Machine Learning Studio, and use the data to train a model to make predictions. I'm going to take a few minutes and talk about different machine learning strategies as I'm exploring strategies to make the gas price prediction. The first piece of this is to look at the patterns in the features to see whether or not there's correlations between different features, to see how the features depend on each other. So in this, on the left-hand side, what I'm looking at is gas price on the horizontal axis, and then a variety of different inputs, the potential inputs on the vertical axis in the different columns. And I see probably the most important piece here is the second graph, which is the price of crude oil, which looks highly correlated to the gas price, the price of the final gasoline. If I look at the correlation between these, I can see this explicitly, that between the crude price and the gas price, there's a very high correlation. This also looks like there's a negative correlation between gas price and the gas stock. which makes sense given microeconomics. The more stocks there are, the more stock gasoline there is, the less I would expect the price to be. Everything else held constant. So it looks like there are some features here that are correlated to the gas price, which makes it a good possibility for doing machine learning on the data. Given the strong correlation between the crude price and the gas price, the most straightforward machine learning algorithm to try is a linear regression. It looks like a fairly linear model to begin with, and so I'm going to start there. This is the Azure machine learning algorithm cheat sheet that shows all the different possibilities on the Azure Machine Learning Studio for things that you can use to train out data. And in our particular case, we're looking at continuous output, so we're predicting values as opposed to classification, so we're looking in the regression chart. And the linear regression is fast training, and it's straightforward to do, so we'll start there and see how well this performs. So looking at a simple linear regression on all my different inputs, I don't limit it to just the crude oil price, but I include everything else to see if I can do slightly better than just the crude price model by itself. And what I see is that I'm doing a reasonable job of predicting the training data and the test data. So I've reserved off the green data points from my training as data that I did not train on, and then train on the remaining blue data points, and then look at the prediction, which is then the orange curve, which does a fairly good job of predicting the test data, the ups and downs of the gas price. And if I plot the predicted price versus the actual price, ideally this would lie on a line, which would indicate a perfect prediction. I'm a little bit off of the line, but I have an RMS deviation of about 15 cents over the predicted price of about $2 per gallon of gasoline. So that gives me a baseline performance for the linear regression model. If I look at then the performance on the test data that I didn't use for training, this is from about the last 6 months or so, from October 2015 to April 2016. I see that the model does a reasonable job of predicting where the price of gasoline will go on data points for which it has had no prior information. The overall RMS deviation is about 9 cents, and the relationship between predicted and actual price is fairly linear. Although I can see that my model is drifting a little bit from the actual data starting in about February 2016. My predicted values are a little bit higher than what actually happens. My second attempt is going to use a support vector machine regression. This is actually not part of the Microsoft Azure Machine Learning Studio, but I'm using RStudio as my model predictor in this case. I wanted to see, to compare to the linear, because the support vector machine can do a nonlinear regression, how that would perform compared to the linear regression. In terms of the predictions, the training of the data and the test data, it does actually a significantly better job. The linear model had an RMS deviation of about 15 cents, and the SVM regression, the scale vector machine regression, has an RMS deviation of about a penny. So it's about 15 times better in terms of predicting the historical data. However, when I look at how the model performs on the data that was not the future data that the model didn't see at all, it does a really terrible job. The RMS deviation is about 26 cents compared to the linear RMS deviation of about 9 cents. And you can see that the model has a giant offset from the actual data itself, which are in green. Those are the actual gas prices. And I tried tuning the hyperparameters for the SVM regression, was unable to get the model to do any better than this. So this is not an improvement over the linear model. Going back to the machine learning cheat sheet, my next attempt is to use a decision tree regression. This essentially breaks up all the possibilities into a binary yes or no, and then builds a set of trees based on these yes-no possibilities, and then weights the decisions in order to come up with the best prediction. So the boosted decision tree regression is a fairly fast training. However, it does take a lot of memory, but I'm not dealing with that on many data points to start with. So here's how the boosted decision tree regression worked on the training data, an RMS deviation of about 1 cent, which is similar to the SVM on the training data, and significantly better than the linear model. One of the nice things about the boosted decision tree regression is that it actually returns information about the relative importance of the different inputs. And this lets me look at how the inputs are impacting the model prediction. And certainly we can see that the crude price has a relative influence of 83.9. So by far the most important parameter in predicting the output of the gasoline at the pump prices. The second most important parameter being the gas stock. I'm not terribly surprised that the third most important parameter being the week. This takes into account the seasonal variations in gas prices. Some weeks the gas prices are higher than others based on U.S. holidays or other annual recurring events, such as the change in the weather that leads to a change in formulations and the change in gas prices. When I look at the performance of the decision tree regression on the data that the machine learning algorithm hadn't seen, there's a little bit of noise in the regression, but it's doing on average a little bit better than the linear model. And so I'm going to go with this model because I have a little bit of improved performance over the linear model without that much cost in terms of computing the model itself. So now I deploy these predictions. I build the model on the Azure Machine Learning Studio. In order to build the model, I'm pulling in historical features and the gas prices to train the data. I train it as a boosted decision tree regression and then score the model so that I have an idea of how well the model is working. From there, I deploy it as a web service via the Machine Learning Studio. It's fairly straightforward to adjust the import data so that I'm only pulling in recent features and then send the data as a web service output that I can then query using the Data Factory and use that endpoint to make predictions on new data as it comes in. So that's the last piece, is that as we get a new data set with an additional data point, the Azure Data Factory then queries that endpoint from the Machine Learning Studio and makes a prediction on the new data. I also have, so in terms of the pipeline, this is where the scoring activity happens, where we pull the data from the output from the pig script, where I have cleaned the data from Hadoop and now send it through the machine learning scoring and get a value for the output data. So what I get in terms of output is I get a scored label, so that tells me what the predicted price, what we would predict the price would be. And I also keep track for that period of time what the actual prices were, so that I can see how well my model's doing. The last step is to deploy the results to an Azure SQL Server, and this will enable me to take that endpoint of that data and display it in a straightforward way in a Power BI dashboard. So I designed and built a Power BI dashboard that allows me to look at these KPIs. I've got the crude oil spot price. I've got the variety of different inputs, how many days supply of gasoline, the oil imports and outports, and refinery utilization. So in a single dashboard, I can watch the big picture of what's happening. I also have the previous gas price in the upper right-hand corner, the previous week's gas price, and then I make a prediction based on the machine learning algorithm what the gas price will be in the middle on the right-hand side. So last week the gas price was $1.99. This was in January 2016. It's predicting for the next week starting on the 17th that the gas price will be $1.65. So we're looking for a slight decrease in the gas price. And it turns out that the actual gas price for the following week was $1.92, which is not as much a decrease as the model was predicting, but it was still in the right direction. So in summary, I built an Azure Data Factory batch pipeline to automate the pulling of the data, the scoring of the data, and then output to the dashboard, so that this, as an operationalized solution, sits and runs in the background every week. It pulls off new data, allowing the decision makers to keep an eye on what's happening. I looked at a variety of different machine learning models and found reasonable performance on the test data, and then used that to build a machine learning model in the Azure Machine Learning Studio, and finally built a Power BI end user dashboard that contains the prediction and allows the users to monitor the overall situation. Thank you for listening, and if you have any questions, comments, or are interested in further conversation, feel free to contact me on my LinkedIn profile.